In this example, we will use the Profile Builder in StarDrop's MPO Explorer module to derive a multi-parameter scoring profile based on a dataset initially described by Wager. The authors used this dataset to develop a multi-parameter optimization method for selection of compounds intended for CNS indications. The CNS MPO score, derived by Wager, is calculated as the sum of the values of desirability functions for 6 physicochemical parameters: calculated log P, calculated log D at pH 7.4, molecular weight, topological polar surface area, number of hydrogen bond donors, and the pKa of the most basic center, resulting in a value between 0 and 6. The authors compared the CNS MPO score for a set of 119 marketed drugs for CNS targets with 108 Pfizer CNS candidates and found that 74% of the marketed drugs achieved a desirability score of greater than or equal to 4, compared with only 60% of the Pfizer candidates. The scoring profile derived by MPO Explorer will contain one or more rules corresponding to combinations of properties that significantly increase the chance of identifying a drug. We will compare these with the results of the CNS MPO score. From the File Open menu, open the file cnsmpo.add. The dataset contains 227 compounds, 119 drugs for CNS targets, and 108 Pfizer's development candidates that did not reach the market. For each compound, 6 properties have been previously calculated, labelled MW, ClogP, TPSA, ClogD, HBD, and pKa, as described previously. For comparison, the CNS MPO score, as defined in the paper, is also included in the dataset. We will use the data in this set to find a scoring profile based on these simple properties with which to distinguish marketed CNS drugs from unsuccessful candidates. In StarDrop's Scoring tab, click the Build Profile button under MPO Explorer. The MPO Explorer wizard will be displayed, enabling us to control the profile building process. We would like to build a profile based on the categorical objective in the Set column. Therefore, choose Category under Objective Type and confirm that the Objective column is defined as Set. Note that the desired outcome is high, i.e. we would like to maximize the value of the objective. Click Next to move on to the next page, Define Categories. Here we can define the order of the categories from the lowest at the top to the highest at the bottom. Remembering that we have chosen to maximize the objective, we need to order the categories such that the drug is at the bottom. Therefore, select the drug category and click the down arrow. Click Next to move on to the Set Selection page. Here we can define the parameters for splitting the data into training, validation, and test sets. In this case, we will use the defaults, putting 70% of the compounds into the training set and 30% into the validation set. Ideally, we would like an external test set, but given the small size of this dataset, it is not practical in this case. Click Next. On the Select Properties page, we can choose the properties that we would like to explore to identify a scoring profile. In this case, we would like to use the 6 simple compound properties as described previously. However, we should untick the CNS MPO score property to avoid using this. Click Next to move on to the last page. The Profile Parameters page enables us to specify some additional conditions. In this case, we will use the default minimum profile coverage of 20%, i.e. we will only consider rules that are applicable to greater than or equal to 20% of the compounds in the dataset. Set the minimum desirable category to drug. This is used to calculate the performance statistics for the rule's ability to distinguish desirable and undesirable outcomes. This parameter is most useful if the objective is a continuous property or has more than 2 categories. Finally, click Finish to begin the profile building session. Once the first rule has been found, this will be displayed within the MPO Explorer Profile Analysis window. The rule is shown in the top right. In this case, the rule suggests that compounds with a molecular weight less than 322, a most basic pKa less than 9.9, and a ClogP less than 3.33 will have an increased chance of success. The criteria for molecular weight and pKa are slightly more important than ClogP. Below this, the statistics for the corresponding multi-parameter rule can be seen. In this case, the mean improvement for compounds obeying the rule is greater than 67%, i.e. compounds that meet these property criteria have a 67% greater chance of being a drug than a compound selected randomly from the set. If you hover your mouse over this statistic, a tooltip will display additional information. The p-value for this rule is 0.0002, suggesting that it is highly statistically significant, and the odds ratio is 10.4, meaning that the compounds meeting all three property criteria have approximately 10 times higher chance of success than compounds that do not. A detailed report on these statistics can be generated by clicking the View Report button. On the left, plots show the rule in property space, corresponding to the property criteria. The properties that are shown are controlled by the tick boxes in the bottom right of the analysis tool. In each plot, the blue lines indicate the boundaries implied by the rules. These boundaries can be dragged to modify the criteria, and the statistics will be updated instantly. The compounds in the training set are represented by circles, and those in the validation set by X. Desirable compounds, i.e. drugs, are shown in yellow, and undesirable compounds, i.e. unsuccessful candidates, are shown in red. Grey points indicate compounds which have been filtered out by criteria other than those represented in the plot. If you do modify the rule, you can easily reset it to the values found by the profile builder. In this case, we will accept the rule that has been generated automatically, and to search for a second rule, click Find Next. The second rule depends only on C log D and pKa. In this case, the mean improvement is only 20%, and the corresponding p-value is 0.15, suggesting that this rule is not statistically significant. Therefore, we will reject this rule by clicking Discard. The final profile, which in this case contains just one rule, will be displayed, and we can accept this by clicking OK. The scoring profile we have just built is now displayed in the Scoring tab. As with any scoring profile, we can modify, rename, or save the profile. Clicking Analyze under MPO Explorer will return to the MPO Explorer Profile Analysis tool. Note you can analyze any scoring profile, not only those built using MPO Explorer's Profile Builder. Run the new scoring profile on the full dataset by clicking the arrow button on the Scoring tab. Note you can ignore the warning about data with zero uncertainty. We can compare the performance of this scoring profile with the CNS MPO score by plotting a Receiver Operating Characteristic, or ROC, plot. Go to StarDrop's Visualization tab and click on the ROC plot button. Choose Set as the property and Drug as the desired result, and use the new scoring profile-set as the classifier. We would like to see a ROC curve above the black identity line, which itself corresponds to the performance of a random selection, and ideally as close to the top left corner as possible. A higher area under the curve, AUC, corresponds to better predictive performance. Here we can see that the AUC for the scoring profile we have generated is 0.69. We can compare this performance with that of the CNS MPO score. Detach the ROC plot for the scoring profile by clicking the Detach button in the bottom right of the Visualization tab. Now on the Visualization tab, change the classifier to CNS MPO score to create a ROC curve showing the performance of CNS MPO score. From this, we can see that the performance of CNS MPO score is not as good as the scoring profile we have generated, because the ROC curve is closer to the identity line and the AUC is lower. However, this is not a fair test of CNS MPO score and the new scoring profile that we have derived for two reasons. Firstly, compounds nominated as clinical candidates will generally have reasonable properties, so we would expect it to be quite challenging to distinguish candidates from successful drugs based on these simple properties. A more realistic test would be to distinguish drugs from early lead compounds from drug discovery projects. Secondly, we have assessed the performance of the scoring profile on the same set used to train and validate the corresponding rule. Therefore, the measure of performance may be artificially high. To address these concerns, we can apply these scoring approaches to an independent test set. From the File Open menu, load the file cnsmpotest.add. This dataset contains 118 drugs, different from those used to find the rule, and 1,000 compounds randomly selected from Chembl, with a pKi or PIC50 of greater than 6, i.e. a Ki or IC50 less than 1 micromolar against the CNS target. The target and measured pKi or PIC50 of each compound from Chembl is included in the dataset. On the StarDrop Scoring tab, run the scoring profile on this new dataset by clicking the arrow button. Go back to the Visualization tab and, as before, click on the ROC plot button. Choose Set as the property, Drug as the desired result, and use the new scoring profile-set as the classifier. Check that the CNS MPO test set is selected in the key below the plot. Once again, detach the ROC plot for the scoring profile by clicking the Detach button in the bottom right of the Visualization tab. On the Visualization tab, change the classifier to CNS MPO score to create a ROC curve showing the performance of CNS MPO score. From this we can see that the performance of the scoring profile is better on this set, achieving an AUC of 0.78. However, the AUC for the CNS MPO score has improved only marginally to 0.63, indicating that it cannot confidently distinguish between lead compounds and drugs. This example has used the simple drug-like properties included in the CNS MPO score in order to draw a direct comparison. However, the profile builder can be applied to any data, including predicted or experimental, biological or physicochemical properties that are more directly related to the in vivo disposition or efficacy required in a successful compound. For more examples of some of StarDrop's other features, take a look in the tutorial section of the Optibrium community.